scientists, to this short video. In this video, we are going to look at potential energy. In addition, we are going to be able to identify a conservative and a non-conservative force, as well as what those mean, and we are going to be able to solve for the gravitational potential energy, as well as the elastic energy stored in a spring. With that, let's get started. To start with, potential energy is defined as the energy that's associated with a system of objects that are exerting forces on one another. Specifically, it has to do with the location or position of some of those objects within the system. Let's revisit our sphere of science. As we throw the sphere up in the air, we know that the displacement is vertically upward. However, the gravitational force is vertically downward. Since those are in opposite directions, the angle between them is 180 degrees. We know that the dot product is going to give us a negative result, hence that the work done by the gravitational field on the sphere on the way up is going to be negative. We see that as a decrease in kinetic energy, while the gravitational potential energy is increasing. On the way down, we see that the displacement is downward. The gravitational force is also downward. Those are in the same plane, they are parallel. Therefore, the dot product will yield us a positive 1, and the work done by the field on the object is positive. This is shown as an increase in kinetic energy, while the potential energy is decreasing. Therefore, putting all of that together, we see that the change in potential energy, delta U, is equal to the negative work done by the field on the object. Put a big fat asterisk down in your notebook. This is the work done by the field on the object. It's not the work done by me as I raise or lower the object. This is the work done by the field. The change in potential energy is equal to the negative work done by the field on the object. Conservative forces are defined as path-independent forces. This means if you have an object and you create any closed path, you end up at your starting point. So the net displacement is 0. The work done by the force, specifically a conservative force, is 0. So examples of path-independent forces, i.e. conservative forces, are gravitational forces and spring forces. Gravity doesn't care how we get from point A to point B. All it cares about is the difference between point A and point B, whether I go on a straight line, whether I move some squiggly path, however I get from point A to point B, doesn't matter the path because gravity is a conservative force. Non-conservative forces, therefore, are forces that do care about path. They are path dependent. If you make any closed loop and get back to your starting point with a non-conservative force, the net work done by that force is not 0. Those common examples of our non-conservative forces are going to be friction and air resistance, which we know is just another form of friction. So friction is the main one that we have to deal with. Let's start to look at how we can calculate the gravitational potential energy and the spring energy. So consider a conservative force F that does work W. The change in potential energy is given by delta U is equal to negative W. We already saw that. The change in potential energy is equal to the negative work done by the field on the object. Well, we know that work is equal to the integral of F dot dx, so then delta U has to be the negative integral of F dot dx. When we go to look at gravitational potential energy, we start off with our base integral, F dot dy. I'm changing x's to y's in here, but you get what I'm doing. We know that the force is the force due to gravity. That's the weight of the object, mg. The dot product is going to be a cosine of 180 because in this case, my object is rising, the gravitational force is downward, the displacement is upward. It's 180 degrees from one another. With all that, we can pull out our constants, mg, so we are just left with the integral of 1 dy, which is just y, evaluated between our limits of integration, yf minus yi. Putting all that together, we see that the change in gravitational potential energy is equal to mg delta y. Mass times gravitational field constant times the change in elevation. Looking at the elastic potential energy for a spring, again, we start off with the change in potential energy is equal to the negative integral of F dot dx. We know that the force is equal to kx. The cosine is again going to be 180 degrees because we know that the displacement and the force are always in opposite directions for this restorative force. So we're able to pull out k, that's our constant. The negative ones all go away. And then we just have the integral of x dx. Well, we know the integral of x dx is 1/2 x squared evaluated between our limits. So putting all that together, we get that the change in potential energy stored in a spring is equal to 1/2 k xf squared minus 1/2 k xi squared, which is not the same thing as 1/2 k delta x squared. You still have to remember the rules of algebra. Don't forget your algebra. Lastly, I want to point out that you get to choose where you want your arbitrary reference line of 0 to be. Choose somewhere that makes sense for your problem so that one of your values is 0, either the initial or the final. In these examples, I'm showing that the initial positions are 0, so that the initial potential energy is equal to 0, so that my final potential energy is just mgy or 1/2 k x squared, respectively. Put your 0 wherever you want. I don't want to put it there loud, I want to put it up at the ceiling. Fine, do whatever you want, I don't care, but your life will be easier if you are smart about it and put your reference point somewhere where one of your energies drops out. After watching this episode, you should be able to tell me what a conservative force is, give me some examples of conservative forces, as well as solve for the gravitational potential energy and the elastic energy stored in a system. That's all for this episode. We'll see you in the next one.